Okay, good. Thanks for pointing that out. All right, so let's continue. So far in this course, we have done almost exclusively incoherent thermodynamics, which is thermodynamics when the unitary that we that we perform on the system, whatever the system is, commutes to the Hamiltonian of the system itself. And yes, so this is very easy to do, for example, when we have heat parts, because heat parts are themselves incoherent systems. There are no coherences, or there are no off-diagonal elements at all in the density matrix of a thermal state when you look at it in the energy eigenbasis. So just allowing only energy preserving unitaries doesn't restrict us much, because we can do all of the thermodynamics that you've seen so far in the course with the little protocols for cooling, for erasure, and the autonomous thermal machines that we did in the last class, where we had that, in that case, it was H interaction on the system commuted with, I would say, the original Hamiltonian of the system. But now we may want to consider what happens when we want to do a unitary operation that does not actually commute with the Hamiltonian of the system. So I'm not going to do the theory in general, but I'm going to give you an idea of what is the resource that we need to add in order to make this possible, and what properties this resource needs to have. So consider a very, very simple example. I have a qubit, so state 0, 1, and the Hamiltonian of the qubit is the usual, let's say, just one, well, E 1, 1. So there's an energy gap of E between the excited state and the ground state. And I want to perform the following unitary, which, if I'm not mistaken, is called the Hadamard Gate. I want to take the state 0 to the state plus, and the state minus, sorry, the state 1 to the state minus. Okay, and so imagine that my initial state, psi system initially, is just equal to the state 0. I want it to be the case that psi final is equal to the state 1. Oh, sorry, is equal to the state plus, which is 0 plus 1 over square root of 2. Now, this is clearly not an energy preserving unitary, because I'm going from an energy eigenstate to a superposition of energy eigenstates. So it does not commute with the Hamiltonian of the system, and that's very easy to check. So how do I make this energy preserving? Well, the only way to try and do it is to add another system which will account for the energy difference. So this is very similar to when, for example, we had the case that we wanted to cool by swapping the state of these two qubits of different energies, and we managed to do it by adding a third qubit of the plugging energy gap and then doing the swap among all three qubits in the degenerate subspace. So here we do something also very similar, or in a similar respect. I add the following machine. And so my Hamiltonian of the machine is going to be just an unbounded ladder for now. So it's just minus sum from n is equal to minus infinity to plus infinity of n times E and n on the machine. So this is the same as saying that I just have, this is my Hamiltonian, plus 1, n, and the energy gap is E, the same as in the system. Okay, so it's a ladder whose spacing is the same as the energy gap of the system. And I'm going to start with a state of the machine that is, I essentially, for the purpose of the calculation, I could choose any state, and I'm going to choose a very simple one to demonstrate the concept. It's going to be a d-dimensional state spread between m plus 1 to m plus d of the states nn. So this would be something like just sort of a finite, it's a state that has finite support. It exists in a d-dimensional subspace of the ladder. And in that d-dimensional subspace, I've taken it to be a pure state, a coherent superposition of all of the states in that subspace of the ladder. Now, why is this introducing this useful? Well, we know that the states 0 psi m, or actually this, and where psi m can be any state, not just the one I've written, has the same energy as the state 1, and again, this is system, and the lowering operator on the state of the machine. So this lowering operator is, as you might expect, the sum over all n of n goes to n minus 1. Very clearly, it just means that if I raise the energy of the system, I just shift the ladder downwards by one step. So clearly they have the same energy. So now what I do is, instead of trying to do the operation where 0 goes to 0 plus 1 over root 2, instead I do the following. I say that 0 goes to 0, sorry, let me write it as a joint operation. Psi m goes to 0 psi m plus 1 lowering operator on psi m by square root of 2. This is now an energy preserving unitary, but I haven't written the full unitary down, but I can complete it quite trivially, because both of the sides, I have a superposition of energy eigenstates of this energy. And as we know, the property of energy preserving unitary is that it's trivial in all non-degenerate subspaces, but within degenerate subspaces, it can be as general a unitary as you like. So this is an energy preserving unitary. Now, at this point, I haven't proven that I have done what I set out to do, because what I set out to do is a unitary on the system, and what I've given you is a joint unitary on the system and the machine. I can write the joint state of the system and machine in sort of block form. And the way I do it in block form is, so this is the 0, 0, 0, 1, 1, sorry. Yeah, 0, 0, 0, 1 is the 1, 0, and the 1, 1 parts of the density matrix of the full thing. And within each of these, I have psi m by 2. And here I will have gamma minus psi m, gamma plus by 2. That's just gamma minus, gamma plus is equal to gamma minus dagger. And then in the off diagonal places, I will have psi m gamma plus, and gamma minus psi m. Okay, and what I'm going to claim is that this density matrix is approximately equal to a density matrix of the form 1, 1, 1, 1. Oh, sorry, this is all by 2. 1 over 2 tensor psi m of the, well, of the machine that I used. And instead of proving that this property remains is true, what I'm going to do is I'm just going to say, imagine now I measure the system in the plus minus spaces. So this is a way to check whether I've gotten the system to be in the state plus, or whether I've gotten it to be into some arbitrary mixed state that I don't know about. And the way to do it is, of course, I take rho system prime, which is trace over the machine of rho system. And then I look at the probability of being in plus, for example, is just trace of the projecton plus times rho system prime. Okay, the first step is going to give me the state. This is just 1 over 2. This is going to be psi m plus psi m, and this is going to be psi m comma minus psi m, and the last is going to be over 2 and a half. This is rho system prime. And then if I multiply this by the projecton plus, that's just basically multiplying it by 0, 1. Oh, sorry. Oh, actually, I just realized the projector on plus is the state 1, 1, 1, 1 upon 2. Actually, yes. So this is actually a new calculation because I realize in writing the calculation before the lecture, I may have made a little bit of mistake. So this matrix is going to be 1 by 4 of the following. 1 over 2. Oh, sorry. 1 plus this inner product. 1 plus this inner product. This is the minus inner product. This is the plus inner product. This is the minus inner product. And this is the plus inner product here. Okay. And it's always 1 plus, 1 plus. Okay. So this is
I have a question.
Yes.
It's about a row SM.
Yes.
Why is it approximately equal to this tensor product you wrote down on the right side?
This is what I'm trying to.
Okay.
Prove. Well, so there are two ways to prove it. One is to look at the state itself, and the other is to just check what the probabilities of getting plus or minus in a measurement are at the end. So I'm doing the second version.
Okay.
Yes.
Perfect.
And after doing that, I will go back to why the other version can also be seen to be true. Yes. Right. So this is the projector acting on the state, and now I just take the trace to get my answer, and this is now going to be 1 over 4 times 2 plus psi m gamma plus psi m plus psi m gamma minus psi m. Okay, and I want to prove that. So to prove that this is approximately 1 or close to 1. And now we see where the crux is. The whole crux is in the following, is in the inner product between psi m versus gamma plus or minus psi m. And this is easy to see because if psi m is equal to, as I said, 1 over square root of d, sum of n is equal to m plus 1 to m plus d of n, then psi m with the gamma plus or minus is just going to be the shifted operator. So n is equal to m plus 1 plus or minus 1 to m plus d plus or minus 1 of n. But here's the interesting thing. This is a state that is shifted by 1 step, which means that the overlap between them is still going to be there on d minus 1 of the states. So the two states that I've written down here and here, they have in common d minus 1 elements on the same state, which means that this inner product here is going to be, well, I'm going to get a 1 over square root of d times 1 over square root of d in both cases, and then I'm going to get d minus 1 from the rest. Okay. Is this part clear? Or is there a question? Nope. Okay. Yes. So all this is to say is that I've chosen a coherent state of the ladder that is wide enough that when I shift it up or down by 1 step, it still is very close to its original state in the sense that its overlap is approximately 1. In particular, this is equal to 1 minus 1 over d when we write it over. So that gives us that the probability of getting a plus result is equal to 1 over 4 times 2 plus 2 minus 2 over d, which is just 1 minus 1 over 2d, which means that the probability of getting a minus, of course, will just be 1 over 2d. So this state is very close to being in the state that we were aiming for when we constructed a unitary operation. And going back to answer your question, this is similar to seeing that these states here, the raised operator acting on psi m is actually very close to psi m, the same way the lowering operator acting on psi m is very close to psi m. And so since they're very close, could take out psi m entirely from this. Of course, the closeness is measured by actually doing a measurement and seeing how close you are, and that's the calculation we've just done. Okay, so Right. So what we've proven is that we can, well, for sure, given a coherent unitary operation that we want to do, a non-energy preserving unitary operation, we can most certainly do this process, add a ladder and do the unitary operation on the joint state, and it will be energy preserving on the joint state, and we'll end up with something similar to what we want to achieve on the state itself. And we see that there are two requirements of this for this to work well. So the first requirement, which we've already seen explicitly, is that the coherent support of the state should be large of the machine that we've used. Because the larger it is, so, and this is the D that we've chosen as a support of the state. Because the larger the D is, the closer our final state is going to be to our initial state. Now remember, we did the case of 0 going to 0 plus 1, in which case you only needed one sort of gamma minus, just a single lowering operator. But we could, in general, take a state, for example, 0 goes to sum over M, or rather EM, let's say, CM, EM. For some general system, we could start in an arbitrary state and go to a final arbitrary state, in which case you will have gamma minus to the M. You'll have raising and lowering operators of various magnitudes. And so the system itself may not just move by one step, it will move by M steps in general. And then all of this will change to, instead of being 1 minus 1 over 2D, it will be 1 minus M over 2D. And here this will be M over 2D. So in any case, D has to be large. Once we've constructed the unitary operation, we can see how much the energy of the system changes, and we have to construct a state of the ladder whose width is much larger than the largest energy change in the system in order for this to work correctly. But the second thing that we require is that the energy should be high enough. So these are requirements both on the machine, just to clarify. The energy should be high enough from the ground state. And what do I mean by this? So I wrote down this example with unphysical Hamiltonian. In general, you're not going to have n goes to minus infinity to infinity. In general, you're going to have something like n is equal to 0, for example, to plus infinity. This would give you the harmonic oscillator. And you can also pick others which are bounded. N is equal to 0 to n is equal to some very large number m, for example. And in this case, you can still do the procedure that we said, except that we have to have that whatever the starting state of the ladder is, when it exchanges energy from the system, it doesn't hit the bottom of the ladder. Because if it hits the bottom of the ladder, then that means that there is some part of the unitary that we want to do that we cannot do, because the ladder does not have that much energy to give the system. So when we perform the unitary operation we're trying to do, the energy of the ladder, or actually the bottom point of the support of the ladder state should be high enough from the ground state of the ladder so that we can keep doing it and it doesn't hit the bottom. The only way to ensure this remains true is you can occasionally put in energy, in the sense that if you do many unitary operations of this form, at some point you could go, well, I need to put in some energy so that the ladder goes away from the ground state. But these are the sort of two requirements you need when you want to do any energy non-preserving unitary on the system. And this is something that was discussed as catalytic coherence, in the sense that you can have this system which ends up doing the unitary that you want and still remaining quite preserved and close to its original state. And there are two statements you can sort of make about this, and they're both correct. One is the statement that if you are given a sequence of unitaries that you wish to perform that are non-energy preserving, you can find such a system. You just have to choose a large enough dimension and a high enough energy such that it will do all of those unitaries up to an epsilon error. So you can say, given sequence of unitaries, which I can also write as one single grand unitary, and an epsilon, we can find psi m so that rho s final of rho s prime is equal to up to epsilon error us rho s us dagger. So that's the first statement we can make. At the same time, we know that if I just gave you now a particular example of a state that I wish to use to do catalytic coherent operations, it's very clear that I can always find a unitary operation that for which this system will fail, because all I need is just that the unitary operation shifts the energy of the system larger than the support of the coherent state that I'm given, or that I have enough, or shifts it larger than the distance to the ground state. So given psi m, one can find a rho s and a u such that this is not possible. So psi m cannot mimic us on the system. Okay. So this of course spawns an entire field of thermodynamics where you study coherent operations on systems, and you consider what is the type of system you need. You consider what are the bounds on the initial to the final states of the coherent state that you use, plus the system. All of the different paradigms that you considered can be now generalized to the case of coherence once you add in the resource of a coherent state. And that spawns an entire other section of thermodynamics. Okay, are there any questions on this concept or comments? All right. Okay, in that case, let's move on. Finally, let me just check the chat to see if there are questions. Okay, no. Right, so we move on now to clocks.
Sorry.
Oh, yes.
I've got a question. I don't quite understand the equal more or less epsilon notation.
Yes. Right. So there are many ways of essentially talking about the distance between two density matrices, which are just different versions of matrix norms. So the most usual one is the trace norm. So you go the trace norm, the one norm of rho s prime minus us rho s us dagger, which off the top of my head is, I'm not sure how this is calculated. So one of the norms is where you simply take the difference between the two of them, the absolute value, and you calculate the highest eigenvalue of that matrix. Another way of calculating the norm is to just take the eigenvalues of the two matrices and, well, no, that would not give you, well, essentially you have to use any valid matrix norm on the set of matrices, or an induced matrix norm where you take the biggest difference. Well, for example, one norm that you can make is find the maximum of rho s prime acting on rho s prime minus us rho s us dagger acting on an arbitrary state psi, maximum of a psi, and you take the norm of this. This is called an induced norm. Rather than take the difference between the two density matrices, you have them act on the vector space, look at the difference in the vector, either via the one norm or the two norm or any norm, and then look at the maximum value of this. So in general, you just have to pick a distance measure. And once you have a distance measure, you can talk about being epsilon close with respect to that distance measure.
Okay, but it doesn't matter the way we measure the distance. It's just that the distance are small. Yeah.
So the property, I mean, this is a property of norms in general. If something is a valid norm on the set of matrices, then it typically has a property that you can switch between different norms up to a factor. So once one norm is bounded, every other norm is bounded with just a constant factor difference. So,
yes.
Yeah.
Yes. Thank you very much.
You're welcome. Okay, so let's go on to clocks now. Right. So within this lecture and the next lecture, we will seek to speak as much as we can about this. So in the last lecture on autonomous clocks, not autonomous clocks, autonomous machines, we spoke about the fact that a unitary operation itself is not a trivial thing to consider. If I actually have a unitary operation on the system, then what I would do in order to implement it is to find an interaction Hamiltonian on the system such that U is given by the action of this interaction Hamiltonian US on the system, right? That the unitary is given by the exponential of this, which means that we can implement the unitary by turning off this interaction Hamiltonian and turning it on and turning it off at a later time in such a way as to, once you integrate over the effect, you get the unitary operation. Okay, so there are two ways to deal with this problem. One of the ways to deal with this issue was what we did in the last lecture. We said, well, actually, let's just take away time dependence at all and deal with only autonomous machines, where once I construct the machine and I switch it on, it just runs independent of any intervention indefinitely. But of course, this is kind of unsatisfying because all of the thermodynamics that we've constructed and studied, which involves repeated unitary operations, then just stops, just becomes something that is a waste if we don't have a way to consistently do repeated unitary operations and include the resources. So the other way of doing it is to change this explicit time dependence, which is a mark of an external system that is acting upon this system, to change it into transform into physical system. In other words, rather than an explicit time dependence, we actually involve another system into our setup, whose only role or whose main role is to essentially turn on and turn off the interaction Hamiltonian without us having to intervene. So one such example could be, so imagine that I have a spin and I label it by S that sits attached to a particle. So that is attached to a particle P. So I have this particle P on which sits this spin S, and this particle P just moves in a straight line. So it's a free particle. And at some point, it crosses a magnetic field P. So what's going to happen? Well, we know what's going to happen. Once the particle enters a magnetic field, clearly the spin of the particle, the dipole there, is going to interact with the dipole with the magnetic field that is passing through. And once the particle exits this field, the result of that will be some unitary having been done in the spin. So we know that once it passes, as it's passing through, there's an interaction Hamiltonian H int that is proportional to S dot P, the dipole interaction with the magnetic field, and that's going to induce a unitary. And so what we've done now is we've replaced T by X of the particle, because what we did is the position of the particle is essentially the encoding of time. And rather than us having to do anything with respect to time, the particle does it automatically by going through a certain region. So this is the general sort of principle as to how we include clocks into our considerations. And we're going to continue now by looking at different ways of including the clocks, starting from the ideal sort of perfect way of doing this, and then going to more realistic scenarios. Okay, so to start with, I'm going to consider the following Hamiltonian for the clock based on what we just did. So I'm going to say HC is equal to PC, where P is the momentum of the clock. So this is momentum. This is a bit of a different Hamiltonian to what we're used to. Actually, let me put a constant of proportionality. Well, not C. Let's say V0. V0 PC. So this is a bit different from the usual free particle, which is P squared over 2m. Here, this is just a constant times the momentum. And the reason why this is a nice thing to consider as a clock is because of the following. Let's look at the rate of change. So now I'm working in the Heisenberg picture, where I keep the state the same, and I just look at the let's look at the rate of change of the operator x over dt, which is somehow the equivalent of the speed. Now I wish to not make a mistake in the sign. So yeah, it's I. So this is I times hc xc. It's the definition of the derivative of the operators. And because this is just the momentum, we know that commutated with momentum and position is IH bar. This would be a minus IH bar. So this is going to give us in the end a plus V naught. So a constant speed of V naught. The important part is that this is the same for hc equals V naught dc plus V of xc. So this is a position dependent potential. And the reason is because, of course, the commutator of h with x, if I put in a position dependent potential here, any function of the operator x also commutes with x. So that's not going to change the commutator at all, which means that I can, for this Hamiltonian, I can put in an arbitrary potential that it has to go through, and the speed of this particle will remain exactly the same as it crosses through the Hamiltonian. Okay. Right. So now what I wish to consider is, well, what happens if I have such a particle like this? Let's say I started, so the particle begins in a delta of something very close to a delta function. So this is psi of c. And then I have a potential V of xc. Sorry, that it goes through. So this is xc. So I start the particle at some point in space. It's moving with the potential V0. So it's not interacting with the potential yet. And then it moves to the potential, and I consider what is psi c as a function here of time. Right? Or equivalently, I can look at the wave function. So psi c of x, which is equal to xc times the state. T is equal to t. Or let's just say t. Okay, now I'm not going to go through this calculation in detail because this will be, I would give you a tutorial problem that actually makes you go through the calculation. But it's very easy to see with this Hamiltonian that as long as it's not interacting with the potential, it's just going to move to the right without changing. So without the interaction, without V of x, you have that psi c of x is psi c of, sorry, x comma t. Comma t is just equal to psi c of x minus v naught t 0. This is just to say that the wave function at a point x is exactly what it was left of the point x as time passes by. But then with the interaction v of xc, what we find is that as the clock moves through the potential, its speed does not change, but it adds a phase corresponding to the potential that it passes through. So what we find then is that psi c of x comma t, where this is within the potential, is equal to, let's say, psi c of x minus v naught t, assuming this is outside the potential, comma 0 times, and it adds a phase, and this phase is just e to the minus I v of x, or let's call this v of y because it's being integrated, dy from x naught minus vt So x minus v naught t, sorry, all the way to x. I'm dealing with units where h bar is 1. It's possible that this might be divided by the speed v naught. I did the original calculations where v naught was 1, so I'm not sure about the constant of proportionality. But what's important is that as it passes the potential, it sort of incorporates the potential as a phase, which means that when it's outside of the potential, so from left of VC to right of VC, we just get that psi c of x just goes to psi c of x comma t goes to psi c of x minus v naught. Let's call it a total time t 0, and just this e to the minus integral over v of y dy. And I'm just keeping over the whole support of the potential. Yeah. What I mean in this whole thing is that, so if my clock is a delta function, of course, then it's very simple. As it moves through the potential, it just gains this phase. If it's not a delta function, and you could consider, for instance, that the clock is the superposition of 2 delta functions, then as each of them move to the potential, they will gain the phase as they hit the potential. So there will be a relative phase difference between the two that's induced by the potential as they move through it at different points in time. But once both of them are on the right-hand side, once again, it just becomes a global phase. So one of the things that you will work out in detail in the tutorial is to see that the end result of introducing a potential on this clock state is that when it goes from the left of the potential to the right of it, it just gains a global phase that incorporates the integral over that potential. Is there any question?
The Hamiltonian that we are using, so it is proportional to just the momentum operator in first order. Usually when you have a particle with kinetic energy, it's p squared. Now we take 1p as velocity v0. Is there, or do you have an example of a system where
yes,
Hamiltonian can actually be of this form, or is this an approximation?
This is an approximation. Yes, indeed. And I will, thanks for the question. So let's see, what is okay, actually, so this is jumping the gun a little bit. I will say that this Hamiltonian is not physical, and it cannot happen in an actual physical system. The easiest way to see it is because momentum itself is unbounded from below, unlike p squared over 2m, which has a ground state. And a Hamiltonian that is unbounded from below is not possible in nature, because any system in such a Hamiltonian would have infinite energy, essentially, or infinite energy to lose. So I am going to talk about how this Hamiltonian is actually, you can see it as the approximation of 2 different Hamiltonians. One is the p squared over 2m Hamiltonian when p is sufficiently high. And the other way of understanding it is as the approximation of a finite Hamiltonian when you make the spacing in a finite discrete Hamiltonian when you make the spacing as small as you like, so that you get a continuous one instead. So I will get to that. But before that, I would like to finish how this can act as a clock when we're doing a unitary operation. Right. So essentially now I'm going to provide sort of the recipe to do a unitary operation on the system using this clock. So we have a unitary on the system, and let's say we know we can write it as e to the minus I h int, and that's it. I'm not going to put a t there, so it's just e to the minus I h int. It's the exponent of some interaction Hamiltonian on the system. So what we do then is we take the total Hamiltonian of the system and the clock to be the following. So you have identity on the system, tensored v naught. Well, I'm going to take v naught equals to 1 here, just so that I don't get the constants wrong, but everything translates into v naught not being 1. Tensor that plus, and this is the key, we have h int acting on the system, tensored some function v. In fact, let me call it g of x of the clock. Okay. And the reason to do this is because this is again something that you will verify on your own, is that in the case when we just had the clock, the result of putting a potential was for it to incorporate that potential as a phase. All that's changed now is that that phase is itself an operator on the system. So what we find then is that if we start with psi of the system tensored some, well, let's say phi on the system, tensored some psi of the clock, which is on the left of G. So this corresponds to, this is G of XC, and this is our psi on the clock, initial state, moving with the speed V0 is equal to 1. Then what we find after waiting for a sufficiently long time is that it goes to the state e to the minus I integral of h int s g of y dy. And this is over the support of G. So this is really exactly the same as in that case, but that was just the clock acting on its own. So the phase was just a phase. Here the phase turns out to be an actual operator, an actual operator on the system. So this is acting on psi on system, tensored psi on the clock. And this in turn, right, we can simplify to e to the minus I, h int on s is just the integral of g of y dy. And these are all on the clock, of course, y is on the clock. So as long as we pick this to be equal to 1, which is just a question of designing the potential so that the total integral is the constant we like, acting on psi system, that's a psi clock, then we get psi system final is just us acting on psi system, and psi clock final is just, well, psi clock translated. So its position has changed, but the state of the system has not degraded at all. So this is essentially a recipe. If I give you a unitary operation, I can convert it into an autonomous operation. And why do I say autonomous? Because here now, this Hamiltonian, if you look at it, it has no time dependence in it. There is an implicit time dependence in the fact that the position of the clock is changing in time, and that's what induces the unitary, but we do not have to do anything explicitly. It can be an entirely closed system, and this will work fine. Okay, there are a few subtleties to mention here. And the first subtlety is that I've assumed here that HS alone is equal to 0. So there is no HS not tensored identity on the clock. Continuing, where was I? Yes, so all of the analysis that I've just discussed assumed that the system didn't have its own Hamiltonian, so that made it kind of easy. The only Hamiltonian that was being applied on the system was the interaction Hamiltonian. If we do have a Hamiltonian of the system as well, then we can potentially have a problem. So let's take HS not equal to 0. Then if now we have the Hamiltonian HSC, identity on system tensor P of clock plus HS0 tensored identity on the clock plus the interaction between them, H int system tensored G of X of the clock. And the problem with this, when you can do the same analysis as before, you can consider evolving by a Schrödinger equation, taking the state of the system and clock as the clock passes through this potential. And what we find here is that, so in general, we know that if we evolve by a Schrödinger equation, what we get is that the rho, well, let's say psi of the system and clock in a small time delta t becomes e to the minus I HSC delta t times psi SC. And then if you do this n times, this just becomes this to the power n. Now, when you consider the influence of this on the system, what you get is that as the clock passes through the potential, it's applying the unitary Hint on the system. However, at the same time, the unitary Hs is also being applied on the system. So now we have a problem. So imagine, for simplicity, that the clock is a delta function, which means that there's no uncertainty as to where in the potential it is. It's always at a particular point in the potential. So if the clock is a delta function, then what we get when the clock moves from the left to the right of the potential is we get the following. So we get, so first you have psi s. First you get e to the minus I h naught s times t, let's call it t left. And this is time until the clock hits the potential. This is basically to say, as the clock is moving, if it's not in the potential yet, the only Hamiltonian that's acting on the system is its own Hamiltonian. Once the clock hits its potential, then you get the following. You get e to the minus I h0 s plus, and now I'm running out of space, plus h int. Sorry, let me just write this with much more space. E to the minus I h0 s plus h int times g of the y of the clock. And this is now just a function because I'm only acting upon it with the system. Okay, as a function of t, delta t. So as the clock moves to the potential, you have the effect of the natural Hamiltonian and the interaction Hamiltonian multiplied, of course, by the strength of the potential where the clock is. And then this gets multiplied by the same thing again, but this is now g of y of the clock at t plus delta t, and then y of the clock at time t plus n delta t. So you have the product of each of these interactions, each of which is just the solution to Schrödinger's equation, multiplied together. And the problem with this product is that we know in general, if I have e to the a times e to the b, this is not in general equal to e to the a plus b. Because what we would like to do with each of these products, we would like to do, let's just add them all together, and then we will just have the Hamiltonian of the system. Well, let's put it this way. If h int commutes with h naught of s, if these two, the interaction Hamiltonian commutes with the natural Hamiltonian of the system, then every one of the matrices in each of these exponentials would commute, and we could put all of the exponentials together and add all of the terms. And this whole thing then, if it commutes, this whole thing goes to e to the minus I h naught s times t plus h int s times this integral of over y acting on the state psi. But if it does not commute, then we cannot do this because e to the a times e to the b is, as you just said, is not equal to e to the a plus b. It has also terms from the commutator, which means that we simply cannot say, well, once I have the unitary I wish to apply on the system, then I can just find what the interaction Hamiltonian that I need to act with on the system is. And by designing this Hamiltonian, it will do the task. And this is basically a simple way to understand it is the following. So imagine that I have an example of when this doesn't work. So imagine I have a single spin which sits in the block sphere, and the Hamiltonian of the spin is equal to, well, sigma z, let's say. So h is equal to sigma z. That's the z-axis. That's the x-axis. And that's the y-axis. Okay, so what is the effect of having hs equals to sigma z? Well, we know the effect of this on a general state of the spin is that it precesses around the z direction. So if I start with some state here, its evolution in time is going to be to go, let's start with the state, psi t is equal to 0. The evolution in time is just going to be to rotate in the subspace. Okay. Now imagine that I want to do the Hamiltonian, I want to do the unitary US that rotates around the x-axis. So I want to take this state here to the state on the other side of the x-axis. So I want this to be psi final. Okay. So one of the ways of thinking of doing this, so US is, well, it's just that unitary. I'm not going to write it down. So flip about x. One of the ways of doing this, if we didn't have the natural Hamiltonian of the system, would just be to say, well, let's simply rotate around the x-axis. So I could take h interaction on the system could be, for example, some constant times sigma x. Because if we rotate about the x-axis, then from that, we will, after a pi angle in this rotation, end up in the final state. But what happens if I do hs plus h int, which is equal to sigma z plus a sigma x? The problem with this Hamiltonian is that this is not going to do what we want, because as we start rotating around x, which is what our interaction Hamiltonian does, the natural Hamiltonian of the system is also precessing around z. So in fact, this is going to be a rotation around some axis that is between x and z. So for instance, if my initial state was right between z and x, and I chose an interaction Hamiltonian that was exactly the same strength, then in fact, it will be exactly in the same direction as the spin, and the spin will not move at all. So this is just a simple example of the fact that if you have a natural Hamiltonian of the system and an interaction that doesn't commute, then it's going to do something that's not as simple as just taking the interaction on its own and looking at its effect over time. On the other hand, if I did have a Hamiltonian that commuted with sigma z, which in the case of a spin is very simple, it's just going to be another Hamiltonian also proportional to sigma z. So for instance, if I had h int on s is some a times sigma z plus, let's say, b times identity, because identity as well commutes with sigma z, then I could easily consider the effect of h int and h naught separately, because they are both rotating around the same axis. So when I join them together, they just rotate faster, but there's no interference in the rotation of one trying to pull you away from the rotation of the other. Okay, is there any question on this? Okay, just before, right, so before the break, I would like to one final comment on this. So indeed, it is more complicated when we have the case that the interaction Hamiltonian of the system that we like to do does not commute with the natural Hamiltonian of the system. Having said that, if we just write down some general interaction Hamiltonian of this form, and we consider the evolution of the system and the clock under this potential, and this is also something that you will see explicitly, you still have the case that once the clock passes through the potential and gets to the other side, you will have the case that the clock state itself is undisturbed. So psi final on the clock is equal to the translated version of psi initial on the clock. It's just that the unitary operation that has happened on the system is not in general equal to e to the minus I h int of s times some constant. And this is because, as we discussed, it's not trivial because there's a commutation relation between these two. However, there is some unitary that is performed in the system. So it just means that in the case that they do not commute, when the unitary operation that we want to perform in the system does not commute with the natural Hamiltonian, rather than just take the logarithm of the unitary that we want, what we have to do in this case, so if we have US HS0 not equal to 0, then what we have to consider is US equals to e to the minus I h naught s plus h int s, and we have to solve now for this interaction Hamiltonian. So we have to do it the other way around. We have to consider what what unitaries are done by putting in an interaction Hamiltonian, even though it does not commute with the system, and then see the unitary operations we get and pick the interaction Hamiltonian that gives us the final unitary operation. So this is not to say that it's impossible to do things that do not commute with the Hamiltonian of the system. It is still possible as long as we pick the correct interaction Hamiltonian. Okay. Right. Are there any questions so far? Okay. If not, we can take a break now, and then let's say till till 5 o'clock or 1700 hours. So that's 30 minutes from now. And then when we come back, I will talk about how this is an approximation to a couple of real Hamiltonians and how to understand these Hamiltonians. I will return 5 minutes before the break so that we can discuss anything. All right, see you in 13 minutes.
Is it right to think of this wave or this delta wave function as the pointer of a clock, or say in analogy to the unitary that at the beginning we wanted to implement, like e to the minus IH t, and t is then the time, and this is then replaced by the definite position of our wave function we introduced.
Exactly, yes. If the clock is a delta function, then what we have done is we have exactly replaced the parameter t by the position of the delta function, which changes constantly. So we replaced, t changes at the fixed rate, of course, by another degree of freedom that changes in exactly the same fashion. Yes. The interesting part is when the clock is not a delta function, then of course, as the clock is moving through the potential, the joint state of the system and the clock is entangled, because different parts of the clock have induced different potentials at that point on the system. But once it moves from left to right, then we can make a few statements about it. So in the case of commuting Hamiltonians, where the interaction and the normal Hamiltonian of the system commute, then it doesn't matter how wide the initial state of the clock is, as long as it was started outside of the potential and ends outside of the potential, which just means we need to wait for long enough time, we will have exactly the effect that we want still. But in the case of the Hamiltonians not commuting, then we have a problem, because as different parts of the clock get to the potential, there is a different amount of the natural Hamiltonian of the system that is acted by that point, which of course does not commute then with the effect of moving to the potential. So then it becomes it becomes a more complicated scenario, which basically means that in the case of non-commuting interactions, we would really like that the clock starts out very thin, so that it doesn't have this problem of various parts of the state inducing the interaction on the system at different times and which do not commute. And that of course requires to have a bigger spread in momentum, which effectively is a higher energy of the clock. Yeah.
Okay, and we do, or say this description here we introduce is to model, say, the setup where we have access to the system, and we also have a physical clock, which is then this additional system we introduce. But our description in the end still uses some background time to also evolve our clock.
Yeah.
I mean,
yes,
we are not to get rid of
the background time. No, because I mean, what we're trying to get rid of is us doing things dependent on background time. But we still have it's still, I think, all of physics, we have the case that we look at a scenario and we see how it evolves in background time. So that's still happening. But what we want to eliminate is us having to change. Effectively, what we want to do is to write down a time independent Hamiltonian. Because once I write down a time independent Hamiltonian, it means the system is closed and there's nobody interacting with it. And that's the goal of this sort of setup.
Oh, yes. Yeah. maybe regarding the lecture notes, will you update them for the Lernphase in summer for the preparation of the exam?
Yes, yes. So the problem with the lecture notes is that I'm writing them sort of partially each week as I prepare for the lecture, but I'm not able to complete them before I have to prepare for the next one. So I will, once these lectures are over, I will use the time that I have in May where I'm not lecturing to complete them and put them up. Yes. So we will have them surely before the end of the course, and definitely much before the exams. Yeah.
Okay, that's great. They're very helpful. Thanks.
Thanks. Okay, let's continue. For the rest of the lecture, we just have the goal of looking at real Hamiltonians that mimic this. Yeah, so the first one, the first Hamiltonian that actually mimics this is the free particle. So imagine that we have the usual Hamiltonian, p squared over 2 m of the clock plus v of x of the clock. But now we do the following. We say that this value of the momentum is very high. So we start with an initial state of the clock whose average momentum Pc is equal to some, let's call this P0. So this is the expectation value for the momentum that is very high. In particular, it is much greater than the integral of V xc x1 to x2 dx for any x1 comma x2. So this is just to say that in fact, no, this is not what I want. It's just greater than v of x for any x. So this is just to say that the initial momentum is just much larger than the potential that it sees. Also, we want that let's say the sigma Pc, which is square root of Pc squared minus Pc squared. So this is just the uncertainty in the momentum is also much less than P naught. Okay, so this essentially means that we have momentum basis of this particle. We have a state that is sitting at a very high momentum. It's centered at a high momentum, and its spread is also small enough that all of its sort of contribution is from the high momentum states, or most of its contribution is from high momentum states. Then what we can do is we can say H, I'm going to split it in this form. I'm going to say this is P naught identity on the clock plus a little Pc squared. So my little Pc is just the actual momentum, and I subtract the average momentum out of it, okay? Upon 2mc plus v of xc, and this is now this is a constant, p squared over 2mc identity plus p naught over mc times pc plus pc squared over 2m plus v of xc. Now, as we know from quantum mechanics, this just induces a global phase. We don't need to consider it. We can always just do it without this and add the global phase corresponding to this at the end. The second term is actually what we considered first. This is just v naught. So the second term is our Hamiltonian that we were looking at earlier. It's just a speed factor times the momentum. And the third term, this one, the third term is much smaller than the second one. So Pc squared on 2m. And when I say smaller, I mean the effect of acting on the state of the clock. Because remember, the state of the clock is the one that has a large momentum. This is much less than P naught over mc times Pc. And this is based on our initial assumption that our average of P naught is very high, and all of the momentum is from there. So we can check now two things again from this. We can check, like we did for the clock, d over dt of the position of the clock. And this is now equal to what we usually get in quantum mechanics. We'll get P naught plus Pc upon m. But this is equal to P naught by m plus a factor, which is plus PC over M, and this is very small. So this now means that, yes, our particle is not one with precisely constant speed, but the rate of change of the speed with respect to the actual speed, or as it passes, the rate, the difference in the speed due to the fluctuating momentum is much smaller than actually the total speed due to just the average momentum, which is a very high number. And another way to check that this remains true is, of course, to check d over dt of PC, which is the momentum of the clock, or actually, let's check of the full momentum of the clock. This is going to be given by, the commutator of P with the Hamiltonian, and the only thing that P doesn't commute with in the Hamiltonian is the potential. So you get something that is proportional to minus dV by dx. And this is going to be, so this means that the total change delta of PC, which is the change in P, is going to be of the order of V. So as the particle moves through any potential that it encounters, the momentum is going to change, but the total amount of change is going to be proportional to the size of the potential. So if that size of the potential is much smaller than the average momentum, then we still have that the change in momentum due to going through potentials is much smaller than the average momentum itself, which in turn implies that the previous calculation we did, where we saw what is the change in the speed of the particle, is also going to be small, because that fluctuating momentum that can change is now bounded by a number much smaller than P naught. The most intuitive way to understand this quantum mechanically is that, as you've probably done in your first quantum mechanics course, if you take, for example, the calculation of a wave that sees a barrier or a step function, then what you get as the answer for the evolution of the particle is that there is a superposition of going over the barrier and scattering past the barrier. This is assuming the barrier is not large enough to actually push it back entirely. So the potential is not higher than the kinetic energy of the particle. So in general, when a particle sees a potential, it changes its velocity. That's number one. It partially passes through the potential and partially gets scattered. All of these calculations are to say that if the energy of the particle is much, much higher than the potential that it sees, then the velocity remains pretty much constant, and the chance of it being scattered by the potential becomes smaller and smaller as the asymmetry between the energy and the potential increases. And so this is the first way of understanding the ideal clock potential, is just a very energetic clock for whom the energies that it sees and the interaction potentials that you put in its way in order to act on the system are small enough that they don't perturb the clock's own evolution. Okay, is there any question about this? Nope. All right. So the next way of looking at the clocks, and this is the one which we will discuss in the next lecture as well, is via finite clocks. And we will use Salecker-Wigner and Peres. So I think it's about in the 1940s somewhere, so a long time ago, right when quantum mechanics was quite fresh, Salecker and Wigner discussed the notion of time and the measurements of time by introducing the following Hamiltonian, which is the one we will consider. So it's just a truncated harmonic oscillator. N is equal to 0 to d minus 1 of n omega n n. So this is just a Hamiltonian, t minus 1, 0, and the gap is omega. It's a Hamiltonian whose basic frequency is omega, but we've truncated it so that you don't have all of the states, you have a finite support space. Okay, why is this? Well, how can this be understood as a clock Hamiltonian? And the reason is simple. I'm not going to bother with the subscripts anymore. Let me consider the following set of states, theta k, which are not the energy eigenstates. They are the discrete Fourier transform of the energy eigenstates. I'm expecting that you've seen the discrete Fourier transform before, but even if you haven't, it doesn't matter. This is the following. e to the minus I 2 pi n k over d n. So it is an equal superposition in terms of the absolute value of the coefficients of all of the energy eigenstates, but it has a phase that depends both on n as well as k. Okay, and k, there are two ways I can consider this. One is to say that k lies between in the range 0, 1, so on until d minus 1. The reason I would do this is because if I add d to k, I will get the same thing. So if I take theta k plus d, then this just by definition is equal to n is equal to 0, d minus 1, e to the I a upon d, and that other term is going to be plus 2 pi n, because k, what I've done is I've taken k to k plus d, and that will just factor out the d over d cancels, give us 2 pi n, which, as you know, is exactly equal to that, because 2 pi n is just e to the I 2 pi n is 1. So this is clearly a sort of a modular set. Starts from 0 to d minus 1, and it returns back to the same. So I can do it in this fashion. I could also alternatively say k can be any integer, with the understanding that I just keep, if I go from d minus 1, I don't go back to d, to 0, I just call it d. This is just semantics, although when you write down the math, you have to be careful as to which one you choose. But anyway, I have these states. The reason these states are useful is the following. Imagine that I do the following. I take e to the minus I, h of the clock, times t, and I put t equals to 2 pi over omega d. Okay. And I act with this on theta k. Then I get, let me just do this, 1 over square root of t, n is equal to 0 to d minus 1, e to the minus I 2 pi nk over d. And now the usefulness of writing things in the energy eigenbasis is that Schrodinger equation and the energy eigenbasis, they're just the phases. And the phases are going to be e to the I times the energy of that state, which is n omega, times the time, which is 2 pi by n omega d n. So each eigenstate, energy eigenstate, just acquires this phase, and this simplifies very simply to e to the minus I 2 pi n over d times k plus 1 n, because the n omega cancels, and yeah, so you just have k plus 1, which by definition is theta k plus 1. What this means is the following. I can sort of write these states on a circle. So let's just label this as theta 0, theta 1, theta 2, so on and so forth. And what I have is that in a time period t is equal to 2 pi by omega d, I have that theta k goes to theta k plus 1. So this is very much the quantum discrete analog of a clock with an hour hand that just moves in fixed periods of time from 1 hour to the next. Yes. Is there any question on this? No. All right. So, right. So we have now a quantum mechanical version of our hand clock, which seems very nice. The reason that this fails to be as good as what we would consider a classical clock with continuous time is the following. What happens if we have t is not equal to 2 pi by omega d times some integer? So we know that in 2 pi by omega d, you go from one, I will call these, let's say, well, actually, let me call them Peres states, because Peres is the one who studied them in a bit more detail. So I go from one Peres state to the other, and so on and so forth in integer multiples of this time. But what happens if I do something in a non-integer multiple of this time? So for example, t is equal to 2 pi by omega d times half. So I start in a Peres state, and I do the time evolution for half of the time that it takes me to go to the next Peres state. So then my question is, so theta k goes to well, in general, I know that I can always write whatever state it is as some superposition ck of the theta k. This is just generally, I can write any state in this form, of course. For the integer units of this special time, ck is just one or zeros everywhere else. But in between, what it turns out that ck is, so if I plot ck, let's say as a discrete plot of k, so this is 0, 1, 2, 3, 4, 5, ... Then what we get is that, so imagine that I started at theta 2, so theta 2, and then in 2 pi by omega d tends to half, I go to this set of to be, as we expect, the biggest contributions are between 2 and 3. So the biggest contributions in superposition are the two states that it's in between, but the other states are not 0. So we get something. So, I mean, if I were to draw it as a continuous function, it would look something like that. And it's the form of it is it's related to the sinc function, which is the sine x over x and stuff. But that's not important. The important part is that in times between the times where we expect it to be at one Peres state or another, there are two things to note. One is that it cannot, of course, quantum mechanically cannot just jump from one Peres state to the other, because quantum mechanical evolution is continuous. But even more importantly, it's not that it remains only in the support of these two states. No, it spreads to all of the states, and then it comes back, sort of recompresses back to the Peres state just in time for the specific unit interval of this special time that it takes to go from one Peres state to the other. In fact, if one were to look at the average of the spread in the theta k basis, and this is something that's a bit tricky to define, because remember, theta k is modular, but you can do this by starting it at a state that is somehow in the middle of whatever modular range you set, and just looked at it from that state to the next, and seen as the state expands, or rather sort of becomes a superposition of all of them and then recombines at one of them, you can look over time at what the average of the spread is, what the standard deviation is. And this turns out to be of the order of square root of the dimension. So that's how much it actually spreads. So if I had a 100-dimensional clock of this form, we can expect that if I just look at the clock at some random time and I just ask what is its spread in the basis of states, assuming that I started in one very specific Peres state, well, the average spread is going to be square root of 100, which is like 10 states. So it spreads to quite a few of the states and returns. Is there any question? Okay, so because the Peres states have this quality of spreading and returning, they are not somehow the ideal states to look at, because, well, let me put it this way. If I wanted to now use such a finite clock and say, well, let me do a unitary acting on the system by using this finite clock, well, what would I do? A Hamiltonian now is in the well, I've written down a Hamiltonian, so the basis of n is the energy basis, and I have the discrete Fourier transform that gives me the theta basis. So these are the time states. This is exactly the sort of discrete version of having the momentum in the case of the ideal clock. So in the case of the ideal clock, this was the momentum of the clock, and in the case of the ideal clock, the time states were represented by the position of the clock. So whatever we did with the position in the case of the ideal clock, we're going to do now with the time states. So one very simple thing to do is to say, let my interaction on the clock be equal to some function in the time state basis. So it's going to be sum over the k of vk theta k theta k. So this is somehow introducing a potential, let's say like this. This is some v of theta. So there's a potential that exists on some support of these time states. And the reason we do this is intuitively clear. We want that the clock, we understand that the clock somehow moves on this circle between these time states. So as it moves on the circle, when it enters the potential, it can trigger unitary, just like we saw in the case of the ideal clock. And then when it exits the circle, it finishes doing this unitary operation. The problem that we have is that we know that it's not just the case. If we started, for example, at θ0, it's not the case that we would have to wait a really long time before we got into the potential, because we already know that at times between 0 and t1, where we expect to find it at 1, it will already be in a superposition that will have some support everywhere on the circle, which means that the potential will already be acting. And because the potential on the clock, which is in the theta basis, does not commute with the Hamiltonian of the clock, which is in the n basis, this means that the clock itself is not going to be preserved under this operation. So here's where we see the effect of having a real physical, well, when I say physical, I don't mean, I'm not describing an experimental setup, but I'm describing a Hamiltonian that can actually exist in nature. And the result is that the clock itself is not necessarily preserved by using it to trigger an operation on the system. Okay, I'm not going to go, I leave going into the details of doing this and arguing how well the clock can do this on the system into the next lecture. For now, what I'm going to do briefly is I'm going to introduce the idea of using a superposition of states rather than the Peres states. So this is actually related to the work of Misha and myself in the group. This is the quasi-ideal clock. WSO, that stands for Woods, Silva, and Oppenheim. And the idea is basically the following. Rather than start in a Peres state, we start in a superposition, specifically a Gaussian superposition of Peres states. So we say, let psi of the clock be equal to some superposition from k is equal to, let's say, k naught minus d over 2 to k is equal to k naught plus d over 2 minus 1 to make sure that it's exactly d states. And we go e to the minus k naught squared over sigma squared e to the minus I 2 pi n naught k over d times theta k. So I started with a superposition of the angle states. One thing important to see is if, and here just for simplicity, I assume that k naught is an integer. So k naught is an integer. Otherwise, this will be, might be slightly, well, the summation has to be over integers. So k naught is an integer. It's not necessary. I could choose k naught to be somewhere between integers. Then I just have to use the roof and ceiling functions to go to the closest integer when I write the sum. But assuming k naught is an integer right now, I see that if sigma tends to 0 in this above state, then what I'm going to get is that the only non-zero coefficient is, sorry, if sigma tends to 0, the only non-zero coefficient is going to be at k naught. Sigma tends to 0 means the Gaussian has become infinitely thin. And so then I would get psi c is equal to theta k naught. So this family that I've written down includes the Peres states. If I take the variance to be going to 0, I would get back a Peres state. And if sigma tends to infinity, so that this Gaussian factor is actually the same for all of them, then I would get that psi c is equal to the sum over k of e to the minus I 2 pi n naught k over d theta k. And this, in fact, if n, well, there is some constant of proportional outside, of course, for all of those to remain sure they're normalized. Yes. If n naught is actually an integer here, then what we get is we end up doing the inverse discrete Fourier transform. So if n naught is an integer, then we end up getting n naught, I think, modulus of the dimension if n naught is very large, but assuming it's not, then it'll be between 0 and d. But we get an energy eigenstate. So this is to say we've constructed here a family of states, which is a general superposition in the time basis. And we can just tune this parameter sigma. If sigma is 0, we get the Peres states. And if sigma becomes infinity, we get the energy eigenstates back. Okay, why do we construct such states? The reason is exactly the following. So remember, I just discussed briefly what the average of spread in theta k is. It's square root of d if I start in the Peres state. So what I'm going to do is now I'm going to consider the following. And this I'm not going to do the calculation, but I'm going to argue what the result is. So this is time, and this is the spread in theta. So sigma squared theta, which is somehow the spread in the theta basis. And I asked, what is this spread if I start in the following scenario? So I start in the Peres state, theta k. I start in the quasi-ideal clock state, or I start in an energy eigenstate. Okay, so what we see with the Peres state, so I do this thing. I take the Peres state, I take the quasi-ideal state, which is some Gaussian superposition, and I take the energy eigenstate, and I ask, how does the spread in the theta basis change in time? For the Peres state, I get some oscillating function. And this is precisely, if this is 0, this is exactly 2 pi by omega d, the amount of time it takes to go from one Peres state to the other. In between, it's a superposition of many Peres states, but from the time it takes to go from one to the other, it returns back to 0. And somehow if I took the average of this, so I can represent this by taking sort of a line somewhere inside, this is proportional to square root of d, or it's of the order of square root of d. On the other hand, if I take an energy eigenstate, well, we know the property of an energy eigenstate, it's stationary. It doesn't change in time. So it has some sort of value that's just constant. But it is a very high value, because if I have it, remember my energy eigenstate was formed by an equal superposition of all time states, which means that the variance is going to be of the order of d, because I'm spread over d. And now I ask, well, what is the variance of the quasi-ideal state? The starting variance, unlike the Peres state, is not 0, because I start in a superposition of Peres states. So I start with, let's say, some value here. But it turns out that in the quasi-ideal case, I have an oscillation, like in the Peres case, but it's just smaller. So it's d to some other power eta. So the advantage of taking a Gaussian superposition is that even though it doesn't go to 0 variance, the variance actually fluctuates less than that of the Peres state. And in fact, as d becomes larger, we can make both. So let me call this, let's call this epsilon, the total width of the fluctuation. We can make both d to the eta tend to 0, or well, in this case, tend to 1, meaning that it's always, it looks like it's at a Peres state, or it's just between two Peres states, and all of the other coefficients are essentially very small, as well as epsilon going to 0. And what this means that in the ideal case, I can have a state that basically starts out with as small a variance as I like, but essentially remains there or almost there for all time. All of this is to say the following: if I pick a Gaussian state, one can show that it remains approximately a Gaussian state as it moves. So even though it's actually a discrete state and not a continuous function, the evolution of the state looks as if we just took a continuous Gaussian and we just kept moving it around the circle, and the coefficients of the actual time states are just the points on that continuous Gaussian function as it moves along the circle. This is a much better state to use for the purpose of the calculations we want, because now we are sure that if we start with a Gaussian that's far away from the potential that we have placed on the clock space, then that Gaussian will actually take a while to move through the potential, and the shape of the function will remain approximately the same up to things that we have to calculate as it moves through this function and through this potential. Yes, so in the next lecture, I will discuss this in a bit more detail. Well, when I say how well the clock does, as a function of its dimension and as a function of the unitary it's applying to talk about how well it does and what are the implications of that on actually thermodynamic and thermodynamic resource theories that we've been discussing earlier in the course. But for now, I will conclude at essentially the introduction to what the finite Salecker-Wigner-Peres clock and the quasi-ideal clock state is. Are there any questions on this part?
Sorry, can you repeat
Yes.
what QI stands for?
Oh, this is quasi with a capital I, quasi-ideal. So it's basically close to ideal. Yes.
Okay, thanks.
Yes. Actually, one final thing to say, because actually I wanted to say this. The reason that this can be seen as an approximation of the P Hamiltonian clock is that, so when I have a Hamiltonian that's of this form, 1 over square root of D, n omega, also not 1 over square root of D, just n omega n is equal to 0 to D minus 1, I have these two parameters, D and omega. If D goes to infinity, we get the oscillator. And what this has is that it has an infinite discrete, so infinite discrete energies, but continuous time states. So what I would get then as a result is that the number of time states in the circle just keeps increasing in number, larger and larger, until it just becomes a continuous thing. And this essentially becomes the phase of the harmonic oscillator. So the phase of a harmonic oscillator. On the other hand, if I keep D the same and I take omega tends to infinity, then I end up with discrete times. Well, actually, no, this is not the thing I want to do. If I consider that omega goes to infinity and D goes to infinity, but in such a way that omega by D goes to 0. So sorry, and this is the reason why I got confused. I want omega to go to 0. Let me do this properly. If omega goes to 0 and D remains constant, then I end up with continuous energies, but discrete and finite number of time states, which is not very interesting. The interesting part is to take D to infinity and omega going to 0 in such a way that the gap between the time states also decreases. And off the top of my mind, I'm not exactly sure. I think it's omega D also must go to 0 infinity. I'm sorry, I will confirm this for the last lecture. But this, what this will do is it will take us into a Hamiltonian whose D going to infinity means that the, omega D also goes to infinity. So if you write down a Hamiltonian in this form, where these are all of the states n, then D going to infinity means that this has many of them, and omega D going to infinity basically means that the spacing between them also goes to 0. Sorry, I will confirm this the next time. This is basically to say that in the end, what we end up with is an approximation to the P Hamiltonian, because we get that both the Hamiltonian itself is unbounded and the number of time states as well become unbounded, as well as the gap between them going to 0. So depending on the different limits of this Hamiltonian for the clock that we've written, we can get back the momentum clock that we discussed as the ideal clock at the beginning of the lecture. And of course, as we see, in order for this to happen, we need that the energy of the clock, the Hamiltonian of the clock, has to go both ways to minus infinity and plus infinity. Okay, that concludes anything I have to say. Thanks for the extra 5 minutes. Is there any final question? Nope. All right. In that case, I will see you all next week for the last lecture, where we'll continue discussing these clocks, as well as look at clocks from the perspective of information theory for a bit. Thank you, and see you all next week.